So good morning, everyone. Thank you, Ruslan. Thank you to the organizers. I'm just delighted to be here in Moscow, and I'm delighted to be part of such a wonderful program. It looks like we're going to have a very nice time here. The work I'm presenting today is joint work with Marshall Berman at the Genie Project Office and with many collaborators on the Genie project and worldwide. You'll see I have down in the bottom here the Genie logo. This is because I come from the Genie project. So I'm going to speak in three parts today. I'm going to talk a little bit about what future internet and distributed cloud testbeds are and why one would want them in the first place. I'm going to talk a little bit about the Genie project and how we've built a specific testbed that itself is a modest-sized federation. And then I'm going to come to the main point, which is to talk about the progress we're making and the challenges we still face in building a worldwide federation of these sorts of testbeds. So I'd just like to begin by saying I'm reporting on the work of many, many people. So anything that got right is their work, anything that is wrong is my work, and anything goofy I say is not anything that perhaps the United States National Science Foundation would have said. So let's talk a little bit about why one would want to build a future internet and distributed cloud testbed. This is the basic problem. We have a clever inventor with an idea to advance the nature of internet working, and he or she comes to a room very much like this room and proposes this idea. However, it's extremely difficult, and many people have complained about how hard it is to conduct research in the live internet. The internet won't accept your new protocols. Certain experiments you might want to conduct would be harmful. So you arrive at this logjam. I present a clever idea, and people in the room are skeptical, and honestly skeptical. They wonder, will this work? How about security? How about scalability? And there's really no place to go from here. This is the end of the discussion. So this is why one wants to build a testbed to conduct these experiments. We want to be able to try the new experimental protocol, place it into a running network, and see how it works. We want to expose this application to a long line of potential users who really don't care that this work is being done in some sort of experimental network configuration. To them, it's just another application on the phone they're already carrying. But to our researcher, he has his own slice of novel infrastructure in Genie or another testbed. And he's learning every time somebody picks up the phone and uses this app. At the end, our experimental researcher has a great paper, a bunch of new knowledge. There are a whole lot of users who are enjoying this service. They have no clue how it might work, but they're enjoying it. And even the skeptics are convinced. What a great idea this was. I knew it all along. So that's the happy ending version of the testbed story. We won't tell any not happy ending. That's the only version we'll tell today. What do you need to make this possible? And there are two basic concepts that are required to build such a future internet testbed. The first one is called deep programmability. Deep programmability says that I can take my software, my new protocols, and run them not just in my computer in my lab, but I can take that software and insert it into the network, run it all across a large federation of resources. So that's deep programmability. The second key concept is slicing. If we're going to build a substantial testbed and many people are going to use it to run many experiments. It's important that they don't interfere with each other. So when I'm programming my piece of the network, my slice of the network, you could be programming your slice of the network, and we won't conflict. So deep programmability and slicing are the two key capabilities we need to build. So let's look a little bit at one example of the Genie example and see what mechanisms we've used to do that. So within Genie, the basic unit of deployment is called a Genie rack. It contains computation, networking, storage, all in a sliceable, deeply programmable fashion. We group these into what we call aggregates. An aggregate is simply a bunch of stuff, typically in one place, that's being controlled by a single manager. When an experimenter needs to gain resources from the testbed, she goes through usually a software tool on her own workstation. And that software tool speaks to an aggregate manager. The aggregate manager is responsible for giving out resources within the testbed and for administering them. In Genie, compute resources can be either bare metal, raw machines, or virtual machines. And the exact type of virtualization and the exact kind of provisioning is an implementation decision that's left up to the owner of the resource. Our current implementations are using either Emulab software, developed at the University of Utah in the US, or OpenStack software to provision virtual machines and physical machines. Inside a rack, the slicing is implemented simply using VLANs, virtual LANs. It provides a certain level of isolation. It's obviously not perfect isolation. Whenever you work on a slicing situation, you have to settle for the type of isolation that's provided by the virtualization technology you've chosen. In Genie, we also have a number of wireless base stations currently running WiMAX. In the future, good morning. In the future, to be running LTE. These are virtualized too. The base station software simply maps your device ID into a VLAN and then into a slice. Between racks at different slices, we have a wider choice of virtualization techniques for the network. We can simply provision VLANs again. We can use a variety of dynamic circuit provisioning mechanisms. Or we can use OpenFlow to software-defined networking to slice the flow space. Now, for those of you who are interested in sort of OpenFlow details, if you're not, just skip this slide. We began early Genie implementations using FlowVisor. We found it somewhat challenging and complicated. If people have experience with FlowVisor, you probably know what I mean. And it turns out there are similar options that are every bit as useful for the vast majority of experimenters and are stable. So we're moving in that direction. Slicing across Genie, again, VLAN translation, I go backwards. No, I didn't. So to improve the slicing, you can either translate from VLAN to VLAN. You can use software-defined networking to keep the stitching across, or in the future you can switch to software-defined exchanges. None of this would work without an underlying core network that provides the supporting capabilities. In Genie, we're primarily using Internet 2, which is the research and education network in the United States. And we're relying on their advanced Layer 2 services. There's an OESS aggregate manager that is dynamic virtual circuits. And there's a new tool they're calling flow space firewall, which is exactly one of these simpler flow visor replacements. It's another multiplexing proxy for OpenFlow. So those are sort of the slicing mechanisms. Deprogrammability is actually a bit simpler. So deprogrammability of compute resources really simply involves letting the experimenters loose on the full machine. If it's a physical machine, you get root access. If it's a virtual machine, same thing. Install your own operating system, install your own network stack. When you come to programming the network, there are more options. You certainly want to support both internet protocols and non-IP protocols for experimentation. One very popular and lightweight mechanism for implementing deprogrammability in the network is software routers, click, sort, that sort of thing. Install Open Virtual Switch for a full-up software-based switch, or go ahead and program OpenFlow in hardware. These are the sorts of options we're making available in G. All right, so part one, why would you want a future testbed at all? Part two, how did we do it in G? Part three, what progress are we making in federating these sorts of things internationally? So I'd like to make a couple of motivating observations. The first one is that these sorts of testbeds are turning out to be very useful in a wide variety of settings around the world. We're seeing ones showing up here in Russia, we've seen them in Europe, Japan, Brazil. But most of these have national or regional scope, and most experimenters' ideas have global scope. So we need to do some work to make these resources available so that a researcher can extend beyond the limits of the specific testbed where he or she is a member. Those of us who build the testbeds are very interested in seeing researchers from around the world come and use our testbeds so we can be exposed to more of the great ideas. So there's a lot of appeal, both for those who are building the testbeds and those using the testbeds, to find ways to federate them together to support larger experiments. There's a basic technology benefit as well. If I start off with M things, M testbeds, M aggregate managers, M of whatever they are, and N people, and they all want to use these other things, there's this sort of obvious combinatorial explosion of trust relationships. Each of the people has to trust each of these devices, and vice versa, and that's never going to work. It's just too many. And this is the fundamental problem that we confronted when building G, and there's an obvious solution that extends from the national level to the international federation level, which is simply to develop some trust broker in the middle that everybody can trust. And you cut down the number of relationships dramatically. You can, of course, stack these so that you develop a trust relationship among federations, which creates a lot of leverage. It's a little dangerous, but it creates a lot of leverage. That's what we're trying to do with the international federation process, is to scale this process up another level. So how will we do that? 3 basic steps. First, we have to make this decision. Second, we need the technology to do it. Third, we need second, we need the technology to federate the control plane. And then third, we're going to need the technology to federate the data plane. This is the hardest part. The hardest part is making these decisions and working out our terminology so that we agree on what it is we're trying to federate and how it will work. It starts with a clear understanding of what the benefits are to each participant. There's a trust phase, and we need to work on getting our terminology straight. So what we've learned in federating diverse testbeds so far is that policies overlap for a while, and then we run into terminology issues. There are questions that apply in one testbed that may not apply in another. Some of the testbeds we've worked with are very concerned about the allocation of resources. Have I paid for this resource? Do I have this number of compute hours available? Others don't seem to care much. Some care a lot about the purpose to which I'm devoting these resources. Is it academic research, or is this a commercial study? We can handle these policies so long as we've collected the data. However, if you're working in a testbed where nobody's ever cared whether or not you're an academic, and you're not collecting that information, it's very difficult to provide it to another testbed when you choose to federate. So you do have to work these issues out, simply making sure we understand each other's terms and needs. Another basic principle that we've employed is to enforce policy locally. Make end users aware of what they need to do to acquire the resources, but when they present a credential, work at the local resource, at the local aggregate manager, to enforce access and management. There are a number of specific tools that you need to implement control plane federation, but one of the main focuses is the AAA components: authentication, authorization, and accounting. Who am I? Am I entitled to use these resources? And is somebody keeping track so that I can pay my bill, or that if something goes wrong, people can contact me and have me fix it? There are a number of application programmer interfaces currently being developed by an international federation. This group is headed out of the European Union, particularly by Berman at iMines in Belgium. And they're defining the key services: member authority, who are these people, slicing, and monitoring to keep central track of what's going on in the federation. Again, all policy management is enforced locally at each individual resource. I think a key point here is that these APIs and the associated interfaces are being developed by an international team. They are open access, and there are open source implementations available. Please talk to me, or there are references in the paper that will point you to the actual open source implementations for these. Many of the implementations rest on standard existing implementation mechanisms: X509, ABAC, SFA. The data plane federation, as well, is based on standard mechanisms, either on-the-fly VLAN allocation from an available bundle, or dynamic circuit provisioning using mechanisms such as NSI. As we go forward, software-defined exchanges seem to be a very promising mechanism for extending the uniformity of deprogrammability farther down into the network. I think I'll show this picture, which shows the potential growth of current ongoing FIDC testbed efforts that we're aware of. This is a very large community, and there's a lot of commonality here. And we're working very hard to build a multinational group of testbeds. We're seeking new partners, and this is an activity among equals. There remain a number of challenges. We're not very good at describing our resources in a heterogeneous fashion. We're not very good at describing non-trivial policies and enforcing them in ways that make everybody comfortable. But the hardest part's going to remain the human level federation decisions, making sure we understand each other's needs and assuring common benefit. We've made a very good start. We've got a long way to go. I look forward to progressing and advancing this cause with many of the people in this room and elsewhere. Thank you.
Well, now it's time for questions. Questions, please. Okay.
Thank you for your speech. I have a couple of questions now. First, your federation resources and federations or unions of federations. On one of your slides, you told that they have a common terminology. I think it's not exactly terminology. You have to have a common language which is describing policies, because in one country, academic means one set of privileges. In another country, academic means another set of privileges. In one federation, you probably describe computer as a course and memory. In another federation, you're just interested in course and vice versa. So, are there any common language which could describe policies? And is it a point of research in your federations and in your formal rules describing these federations?
So, first, yes, you're exactly right. And this is a very important point. Terminology is important at the level of the human decisions. We need, when we shake hands, we need to know what we're talking about. If we want to make that happen in software and enforce it automatically, which of course we do want, then we're going to need a good deal more supporting technology. And you're right, we need not just terminology, we need ontology, so that we have common language, and we have machine-readable versions of the common language, so that we can enforce them uniformly. And we need, you're correct again, machine-readable policy statements. I think a lot of, and yes, these are all areas where a bunch of research needs to happen. All too often, all of these capabilities are embedded deep down in the software implementation, so that if we're trying to exchange an agreement about policy, we can't really read each other's policies, and I may not even be able to explain the policy implemented in the software terribly well. So you're right on all counts. We need all of those things, and I believe these are two of the key fronts in research and federation. One is resource description and discovery, and another is policy description and enforcement. So yes, you're quite correct.
Еще вопрос, пожалуйста.
So I believe one such language is hexagonal, and it seems to have a similar feature that one of your slides alluded to, that you assume a trusted broker as opposed to an environment where you have, say, distrusting parties sharing policies. So is it baked into the GE project to have trusted brokers?
That's a nice question. I think at some level, one is going to need some amount of trust, Right? It doesn't need to be a trusted broker, but it needs to be a decision that if I issue a credential, you will respect it in some way. But the nature of a policy statement is you may be able to say you'll only respect it so far. And this is why we want to do enforcement locally, right? I bring a credential. I say that the Genie project states that Mark Berman is permitted to do these things. It is permitted to do these things. And then the local resource manager can decide whether or not it cares that there's a statement that says the Genie project says thus and such. Did I address your question?
I didn't phrase it precisely enough, but we can take it.
Okay. Sorry.
One more question. Well, Mark, thank you very much for the presentation.
Thank you very much.
Okay, let me introduce the next speaker, who is John Montbreti.